Welcome back to video lecture on gas dynamics and jet propulsion, subject code MA8096. I am Dr. Ananda Kumar, Assistant Professor, Department of Mechanical Engineering, Government College of Engineering, Tirunelveli. I am going to teach Unit 3, Normal Shock and Oblique Shock. The introduction of the normal shock is when there is a relative motion between a body and a fluid, the disturbance is created. If the disturbance is of an infinitely small amplitude, that disturbance is transmitted through the fluid with the speed of the sound. If the disturbance is finite, shock waves are created. Shock wave and expansion wave normal shock. Shock which occurs in a plane normal to the direction of the flow are called normal shock wave. Flow process through the shock wave is highly irreversible, cannot be approximated as being isentropic. Develop a relationship for a flow property before and after the shock using the conservation of mass, momentum and energy. In some range of back pressure, the fluid that achieved a sonic velocity at the throat of a convergent divergent nozzle and is accelerating to supersonic velocities in the diverging section experiences a normal shock. The normal shock causes a sudden rise in pressure and temperature and a sudden drop in velocity to subsonic levels. Flow through the shock is highly irreversible and thus it cannot be approximated as isentropic. The property of an ideal gas with constant specific heats before and after a shock are related by. So this is the diagram. So it is a constant area duct. Take a control volume. Here flow through the constant area duct. Here Mach number is greater than 1 at section 2 and Mach number is greater than less than 1 at section 2. Here V1, P1 and H1, rho 1 and S1. These are the properties before the shock. Similarly, V1, P2, H2, rho 2, S2. These are the properties after the shock. Okay. So shock wave. This is a normal shock wave. Okay. The assumption of the normal shock: steady flow and one-dimensional, and change in area equal to 0 because shock thickness is small, and negligible friction at the duct. At the duct wall, since the shock is very thin, zero body forces in the flow direction, adiabatic flow since the area is small, no shaft work, potential energy neglected. The governing equation of the normal shock, continuity equation, that is mx equal to my, and so this is and next one energy equation, and using the steady flow energy equation, then T naught x equal to T naught y and H naught x equal to H naught y. Okay, the two remains constant across the shock. And the third one, momentum equation. So the Newton's second law, using the Newton's second law, we get the impulse function, that is Fx equal to Fy. Impulse function remains constant across the shock. And the next topic is the property relation across the shock. First property, temperature, Ty divided by Tx. Here Ty is temperature after the shock, Tx on the temperature before the shock. Using the energy equation, that is H naught x equal to H naught y, and we get the temperature as equation, Ty divided by Tx equal to 1 plus K1 K minus, that is gamma minus 1 divided by 2 mx square divided by 1 plus gamma minus 1 divided by 2 my square. So next property, pressure ratio across the shock, Py divided by Px. Using the momentum equation, we get the Py divided by Px equal to 1 plus gamma mx square divided by 1 plus gamma my square. And the next property is rho y, density ratio, rho y divided by rho x. Using the equation of state, characteristic gas equation, Pv equal to mRT, and we get the rho x divided by rho y is equal to this equation, that is 1 plus gamma my square divided by 1 plus gamma mx square into 1 plus k minus 1 divided by mx square divided by 1 plus k minus 1 divided by my square. And the fourth one, volume ratio, Vy divided by Vx. velocity ratio Vy divided by Vx. Using the continuity equation, we get the Vy divided by Vx equal to 1 plus k my square divided by 1 plus k my square. Here k equal to gamma, that is a isentropic index. Then 1 plus k minus 1 divided by 2 mx square divided by 1 plus k minus 1 divided by my square. Next property, stagnation pressure is P naught y divided by P naught x. For the isentropic index, for the isentropic flow, x equal to 0 x, that is stagnation equal to static. Then we get the P naught y divided by P naught x equal to 1 plus k mx square divided by 1 plus k my square into 1 plus k minus 1 divided by 2 my square divided by 1 plus k minus 1 divided by mx square whole power gamma divided by gamma minus 1. And the next one, entropy change across the shaft. Del S equal to Sy minus Xx. This is the entropy change. So it is we get the entropy change equation. Okay, across the shaft. Next one, relation between mx square and my square. Here mx equal to Mach number before the shock and my Mach number after the shock. And so these are the derivation, and we get the my square and the mx square. Okay. And so next equation prove that ty divided by tx, ty divided by tx. So this is the derivation, and we get the next one, stagnation pressure ratio, stagnation P naught y divided by P naught x, P naught y divided by P naught x. So these are the derivation. And next one, so this is the continuation of the stagnation pressure ratio equation. And next one, velocity ratio. We prove that velocity ratio. Okay, it is a derivation. And the next one important, next important relationship, Prandtl-Meyer relation. Here, this is the this Prandtl-Meyer relationship relate the velocity Vx and Vy and critical critical velocity. The relation between velocity before and after the shock and the critical velocity Mach number before and after the shock is equal to 1. And governing equation for a normal shock. Governing equation. Next topic, the governing equation for a normal shock. Continuity equation, momentum equation, and so these are the continuous. And the next one. So next topic is the Rankine-Cognat equation. The Rankine-Cognat equation, density ratio across the shock. We know the density rho equal to PBRT for upstream shock, and for upstream shock rho x equal to upstream, y equal to downstream. So we get the density ratio, and also we know that the pressure ratio Py divided by Px. And this is the equation, and this is the derivation of the derivation, and we get the Rankine-Cognat equation Py divided by Px. And the next topic, strength of a shock wave. It is defined as the ratio of difference in downstream and upstream shock pressure to upstream shock pressure. It is denoted by eta. So eta equal to Py minus Px divided by Px. Okay, this is the strength of your shock wave. Okay, so then it is a derivation. Therefore, eta is directly proportional to the mx square minus 1. Mx equal to Mach number before the shock. Mach number. The strength of the shock wave may be expressed in another form using Rankine-Cognat equation. Therefore, eta equal to 2 gamma divided by gamma minus 1, rho y divided by rho x minus 1 divided by 2 divided by gamma minus 1 minus rho y divided by rho x minus 1. So from this equation, we come to know the strength of the shock wave is directly proportional to the rho y divided by rho x minus 1. Okay, so strength of the shock wave is directly proportional to the rho y divided by rho x minus 1. So this is the first problem of a normal shock wave. The state of a gas within bracket gamma equal to 1.3 or equal to 0.469 kilojoule per kg Kelvin. So it is a first problem of the normal shock wave in the state of a gas. Upstream of a normal shock wave is given by the following data: mx equal to 2.5, bx equal to 2 bar, tx equal to 275 Kelvin. Calculate the Mach number, pressure, temperature, velocity of a gas downstream of a shock. Check the calculated values with those given in the gas table. Take k equal to gamma value. Here my square, the formula of the my square equal to 2 divided by k minus 1 plus mx square divided by 2k divided by k minus 1 mx square minus 1. Here, so we get the my equal to 0.4928. This is the Mach number after the normal shock. We know the pressure ratio equation: Py divided by Px equal to 2 gamma divided by gamma plus 1 mx square minus gamma minus 1 divided by gamma plus 1. So therefore we get the pressure ratio equation. Pressure ratio is 6.935, and if in the given problem Px equal to 2 bar, therefore Py equal to 13.87 bar, then we know the temperature ratio equation: Ty divided by Tx equal to 1 plus gamma minus 1 divided by 2 mx square into 2k divided by k minus 1 mx square minus 1 whole divided by k plus 1 whole square divided by 2 into k minus 1 mx square. This is the temperature ratio equation and temperature ratio formula. And we get the temperature ratio Ty divided by Tx equal to 1.869. In the given problem Tx is given, therefore Ty equal to 513.975 Kelvin. And next one, velocity ratio Cy divided by Cx equal to 0.269. 0.2. Here we know that Mach number Cy equal to 0.269, Cx equal to 0.269, mx into ax. Here m equal to c by a. Therefore Cy equal to we get the Cy equal to 275.16 meter per second. Okay. And the next problem: an aircraft flies at a Mach number of 1.1 at an altitude of 15,000 meter. The compression in its engine is partially achieved by a normal shock wave standing at the entry of a division. Determine the following for downstream of the shock: Mach number, temperature, pressure, stagnation, pressure loss across the shock. Here in the given data, mx equal to 1.1, altitude z equal to 15,000 meter. Refer gas table for altitude z equal to 15,000 meter. Therefore Tx equal to 216.6 Kelvin, Px equal to 0.12 bar, and Px equal to 0.12 into 10 power 5 Newton per meter square. Then refer normal shock table. Normal shock for mx equal to 1.1, the gamma equal to 1.4. Therefore my equal to 0.9111, Py divided by Px equal to 1.245, Ty divided by Tx equal to 1.065, then P0 y divided by P0 x equal to 0.998. Then P0 y divided by P0 Px equal to 2.133. Therefore Py equal to 1.24 into 0.120 into 10 power 5 Newton per meter. Therefore finally Ty equal to 0.149 into 10 power 5 Newton per meter square. Then Ty equal to 1.067 into Tx. Then finally we Ty equal to 230.67 Kelvin. Similarly, P0 y equal to 0.259 bar and P0 x equal to 0.2564 10 power 5 Newton per meter square or bar. Therefore, next one, pressure loss. P0 x equal to P0 x minus P0 y. Then finally, pressure loss equal to 50 Newton per meter square. Okay.